Hey everybody. So a little bit of a different flipped classroom video today. Rather than going over something new, I'm just going to kind of go over some of the questions on the review that I think you may have some questions about. Obviously, I'll be happy to go over any of them in class, but I thought since we're asynchronous today that this might be helpful for you. So I'm just going to kind of start here. This is page 1. I'm going to skip over the definitions because I think you can manage that on your own. This first question that I was going to talk about here is this decomposition of water question. So it's asking, is energy being taken in or is it being released as water decomposes? So the first thing we have to do is figure out that this is the equation where water is decomposing, where we're going from water to its component elements. And then we have to look at the fact that the energy component is written as a reactant. So that means this is a thermochemical equation. We're putting energy in. So that means that energy is being taken in. This is an endothermic reaction. If we look at the reverse reaction, which is the synthesis of water reaction, we see that energy is a product. So that would be an exothermic reaction. And these two reactions are essentially the same reaction in reverse. So it makes sense that in one, it's exothermic, in the other, it's endothermic. So energy is being taken in. If energy is being taken in, enthalpy change has a positive symbol. Okay. So just skipping down just a little bit, for number 6, it asks us to state whether the change in entropy, so this is disorder, favors the forward or the reverse reaction. So anytime energy increases, that's going to favor the forward. Anytime entropy decreases, that's going to favor the reverse. So we're really just looking at, is there more entropy on the product side or the reactant side? So I'll just do a couple of them. Here we're going from a liquid to a gas. The gas has more disorder, so that's going to favor the forward reaction. If we look at our second example, we're going from something being in solution to being a solid. So that's going to increase order or decrease disorder. So that's going to favor the reverse reaction. And so we would do that for each of these. Here, they're all in the same state. We have gases for all of our products and reactants, but we have more moles of gas on the product side than on the reactant side. And so there's more disorder on the product side. So again, that's going to favor the forward reaction. Okay, so I think we've got the idea on those. Let's go ahead and skip over to number 8. So in this equation, we have ammonia reacting with water to give us ammonium ions and hydroxide ions in solution. This is releasing energy. We can see that the energy component is on the product side. So that means that this is an exothermic reaction, which means that enthalpy does favor the forward reaction. It tells us the sign of T delta S is negative. So since T is in Kelvin, we know it must be the delta S piece that is negative. So that means that entropy is decreasing. So that means entropy favors reverse. Given that delta G is positive, which term is greater in magnitude and therefore predominates, T delta S or delta H? So we can think about this, delta G equals delta H minus T delta S. So we know that delta H is negative. We know that T delta S is a negative. So I have a negative number minus another negative number. If this negative number is larger in magnitude, then we'll have a negative plus something, and it'll still be negative. If this negative number, the T delta S, is larger in magnitude, then I'm adding a larger number to a smaller negative number, and my overall delta G will be positive. Since my overall delta G is positive, T delta S is greater than delta H. The other way we can think about this is of these are just specific heat problems. I think we've all got a pretty good handle on those. Delta H for number 18A, delta H, we're using delta H is equal to, of the reaction, is equal to the delta H of the products, the sum of the delta H's of the products, minus the sum of the delta H's of the reactants. And so we would have products are 458 kilojoules per mole, minus the reactants are 658 kilojoules per mole. So that would equal a negative 200 kilojoules per mole. Unfortunately, all of these numbers are significant, so we're going to show this as negative 2.00 times 10 to the second kilojoules per mole, so that we can show that these zeros are significant. When it asks which is more stable, reactants or products, if it gives off energy, it tells us products are more stable. If it takes in energy, it tells us reactants are more stable. Since this gave off energy, that negative sign, we know that the products are more stable. Also, they have lower energy. Okay, balanced thermochemical equation for complete combustion of acetylene gas. We're going to go through this really quickly so that we can do the other two problems. C2H2 gas. This is combustion, so it needs oxygen. For 1 second. Okay, sorry, had to take a quick break to stop the background noise. So balanced chemical equation. So we know this is combustion, we need oxygen. We are going to produce carbon dioxide and water. So in order to balance our chemical equation, we're going to put we're going to deal with the oxygen first because otherwise we're going to wind up with odd numbers. So we're going to have a 2 here so that we have 2 oxygens and 2 oxygens. That gives me 4 hydrogens. So I need to put a 2 in front of C2H2, which is going to require me to put a 4 in front of CO2, which now means that I have 8 plus 2 is 10. So I'm going to put a 5 here. And we know that this is going to release energy. So I'm going to go ahead and put that as one of my reactants. Okay, it asks me how much energy is released per 0.25 moles of C2H2. Well, this reaction says that it's 13.01 kilojoules per mole of C2H2. So I have 0.25 moles of acetylene gas, and it tells me that for every 1 mole of acetylene gas, it releases 1,301.1 kilojoules of energy. And so that's how we're going to find that number. Now, in terms of C, 3,900 kilojoules of energy, I'm going to recognize that for every 1,301.1 kilojoules of energy, I have 1 mole of acetylene gas. And for every 1 mole of acetylene gas has a mass of, let's see, 2.02 plus 24.02 is 26.04 grams of C2H2. And it's just a stoichiometry problem. Okay. This one is again an application where the delta H of the reaction is going to equal the sum of the delta H's of formation of the products. minus the sum of the delta H of formation of the reactants. We are given the enthalpies of formation of the aluminum oxide and of iron 3 oxide, and the other components are elements. And so we know their enthalpy of formation is 0. Not sure why I have that equation twice, sorry. Okay, number 21 is an application of Hess's law. So I'll go through this one. We have copper 2 oxide plus carbon monoxide yields copper plus carbon dioxide. And we're given these two equations. So anytime I'm working with these, my very first step is to look and see, is everything that needs to be on the reactant side, and everything that needs to be on the product side. So when I look at this first reaction, I have carbon monoxide on the reactant side, which is where it needs to be. I have carbon dioxide on the product side, which is where it needs to be. And I have a delta H for that. Now, the problem with this equation is that I have 2 carbon monoxide and 2 carbon dioxide, and I don't want that. So I'm going to multiply this equation by a half or divide it by 2, whichever way we want to think about that, which means I'm going to do the same thing to the delta H. And so my new equation is going to be CO gas plus 1/2 O2 gas yields CO2 gas, and the delta H is equal to negative 283.05 kilojoules. Now with my second reaction, I have copper as a reactant and I want copper as a product. And I have copper 2 oxide as a product and I want it as a reactant. So I know I'm going to need to flip this equation, but again, I have those coefficients of 2 and I want coefficients of 1. And so I'm going to flip it and multiply it by a half. So flip and times 1/2. So this is going to be multiplied by a negative 1/2 because when we flip it, we change the sign. So our new reaction is going to be CuO solid yields Cu solid plus 1/2 O2 gas, and the delta H is going to equal positive 155.25 kilojoules. And now we're simply going to add these equations together and add the delta H's together. So I'm going to have carbon monoxide gas plus 1/2 O2 gas plus carbon 2 oxide solid yields carbon dioxide gas plus solid carbon plus 1/2 oxygen gas. And we can see that we have this oxygen here and oxygen here. So we're going to cross those out and we're going to wind up with carbon monoxide gas plus copper 2 oxide solid yields carbon dioxide gas plus solid copper. And the delta H is the sum of these two numbers, which I have to calculate. And that gives us a negative 127.8 kilojoules. And that's our delta H. So always just manipulating those equations and then adding up the delta H values. And we'll do the same process here for the synthesis of hydrogen peroxide. And then we'll take that information and we'll use it in a stoichiometry problem to figure out how much energy would be required to produce 17 grams of hydrogen peroxide. Okay, so this question asks, is this favored by enthalpy? So it tells us that it's a positive delta H. So if it's a positive delta H, it's not favored by enthalpy. But it also gives us a negative delta G. A negative delta G means that it will occur spontaneously. If it is not favored by enthalpy, but does happen spontaneously, it must be favored by entropy. And then to calculate the value of T delta S, we're going to use delta G is equal to delta H minus T delta S. And we have that negative 5.4 kilojoules per mole is equal to 18.0 kilojoules per mole minus T delta S. And so T delta S is equal to 23.4 kilojoules per mole. And then it asks us to calculate delta S if we're at 25 degrees Celsius. So temperature is equal to 25 plus 273 to convert from Celsius to Kelvin. So that's 298 Kelvin. So 298 Kelvin times delta S is equal to 23.4 kilojoules per mole. We'll pull out a calculator again, 23.4 divided by 298. Then we have delta S is equal to positive, 78.5 joules per mole Kelvin. If you get 0.0785 kilojoules per mole Kelvin, that's totally fine. I just converted to joules so that I didn't have to deal with all those zeros. And then for number 24, it asks us to calculate the free energy change for the reactions described by the equations below and determine whether it will be spontaneous or non-spontaneous. So we're given delta H, we're given delta S, and we're given T. So we know delta G is equal to delta H minus T delta S. We need to pay attention because we can see that S is in joules and delta H is in kilojoules. So I'm going to go ahead and convert delta S is equal to negative 0.0807 kilojoules per mole Kelvin. All I've done is divide that by 1,000 to get that to kilojoules. So delta G is equal to negative 75.0 kilojoules per mole minus 298 Kelvin times negative 0.0807 kilojoules per mole Kelvin. And again, we have 298 times 0.0807. And we get that delta G is equal to negative 50.95, so negative 51.0 kilojoules per mole. Since this is a negative number, this is spontaneous. Okay. As always, if you have any questions, let me know. See you in class.